In this video, I will discuss the system design of WhatsApp. We'll see how one-to-one and group chat works. We'll see how messages are delivered in real time for online users. And if the person is not online, the messages will be delivered when he or she comes back online. We'll also see how we get the message delivery status like a single or double tick. Also, if we want, we can see if the person is currently online, and if not, when was the person last active. So let's start with the functional and non-functional requirements. So first one is one-to-one messaging, then group messaging, then real-time message delivery for online users, and access messages after being offline. So if a person is online, the messages should be delivered in real time. And if a person is offline, then when the person will come back online, then only the messages will be delivered. And the last one is image or video sharing. So these are the P1 priority 1 requirements. Next, we have the low priority requirements like online or last seen status of a person. Like in the chat window, in the chat page, we can see when the person was last seen or if the person is currently online. Next, sent, delivered or seen status for a message. So we can see if the message is delivered to the server, then we see a single tick. If the message is delivered to the recipient's device, then we see a double gray tick. And if it is read by the recipient, then we see a blue double tick, right? So that means that the message is seen. So this sent, delivered or seen status. But not all the users in our system will be interested in these two settings. So these are little bit less priority requirements, but we'll talk about all these requirements. Few out of scope requirements for this discussion is data encryption. So we should not allow anyone else to read our personal messages. So data should be encrypted. Temporary or permanent chat. So WhatsApp doesn't store the messages indefinitely in their system. Next, delete chats. We can delete chat in our WhatsApp, right? But it's very doable, but I'm not discussing this here. And audio video calling. So we'll not cover this in this discussion. Next, we have the non-functional requirements, which are the qualities of the system. So the first one is low latency message delivery. So low latency and real-time message delivery means real-time means around 300 to 400 milliseconds. So if we can have less than 500 millisecond message delivery, we are good for our system. Guaranteed delivery, we should not lose any message. Billions of users, so this is WhatsApp scale, there will be billions of users. Each user sending average 100 messages per day, let's say. And his system should be fault tolerant and messages not stored unnecessarily. That we already discussed, right? So WhatsApp stores your messages indefinitely on your device until you delete them. So in the client device, the messages are stored. And if backup is enabled, then it will be stored in the cloud. But in the WhatsApp server side, they can only retain undelivered messages for only, let's say, 30 days. I'm not sure about the number, but there will be some time, right? 15 days or 30 days or more than that. So after that, the messages will be deleted. Next, let's talk about the major entities in our system. We'll have the user first. User will have the user ID, the mobile number, and created at when the user was created. It can have other metadata as well. Then client, each user can be using multiple client devices, right? Like mobile, tablet, desktop, and any other devices. So these are different clients. So in the client entity, we'll have the user ID and client ID mapping, and this when the client was added. Of course, it can have other metadata. Next, the chat entity. So here for one-to-one and group chat both, I am using only one chat entity. So basically, if it is a one-to-one chat, it's a group chat with two members or two participants, right? So here we'll have the chat ID. It can have few other metadata, and then we will have the user list, user participant list of this chat. So if it is a one-to-one chat, then in this user list, it will have just two members. And the created at when the chat was created. Next, the message entity. So it will have the message ID, the sender user ID who is sent the message, and chat ID in which chat. Then the content of the message, the asset URLs. So any type of media like image, video, WhatsApp can send a location, contacts as well, right? So any types of media. Uh, and then the timestamp when the message was sent or message basically is received in the server. Next, let's discuss about the high level design here. So consider this chat server via which user will be sending message. If user A wants to send a message to user B, the message will be delivered via this chat server. Consider there is this chat database, it is storing the chat details. So this chat tables we have, it will have the chat ID, the creator ID, who created the chat and when it was created. Of course, it will have few other metadatas. And then chat participants table, it will have the ID, the user ID and chat ID. So user ID and chat ID combined, it will be unique. And then when the user was added as a participant for this chat. Next, we have the message table. It will have the message ID, the chat ID, the content of the message, the sender ID who has sent the message, asset URLs. There can be multiple assets. We can have a separate asset table as well to keep this mapping. And then the timestamp when the message was received and the status of the message, whether the message has been delivered or not, and different other statuses. Now, how the message will be delivered. So, user A will send the message to chat server and chat server will send the message back to user B. We'll come back to this connection part, but before that, let's discuss about how the media will be uploaded quickly. So, media, let's say this asset server will take care of any media or asset uploads. And of course, this medias will be stored in some blob storage or let's say S3. And this upload happens via pre-signed URL. So user directly via this server doesn't upload the media because that will add some delay. And of course, there will be, if we add load balancers and all here, so there might be some size limit for the media. So considering that, when the user wants to upload something, will fetch one pre-signed URL from S3, will pass it to the user and user will be directly uploading the media using that pre-signed URL. This pre-signed URL of course will have some expiry time. Before that only the media has to be uploaded. Now coming back to the message delivery. So if the user B is online, then the message directly will be delivered to the user B in real time. But if the user is offline, then we have to store the undelivered message in our system. Of course, we have this message table, right? So here we have the chat ID and the sender ID who has sent the message. So just as we have the chat ID, we know the chat participants, but we have the sender ID as well. So we know who all the recipients are. But it can happen that few of the recipients are online and few are not. If it is a group chat, if it is a one-to-one chat, maybe the recipient is online or offline. Both can happen, right? To make things easier, I have introduced one more table. It is having the message ID and the receiver ID. So if the recipient is not online, it will be stored, the message will be stored in this inbox table. When the receiver or recipient will come online, the message will be read from this inbox table, and after that the messages will be deleted from this inbox. So if one message is delivered in this chat, right? So if this chat has multiple participants and the message is delivered to all the participants, then we can change the status to like delivered. Otherwise, it will be partially delivered or something. So now let's discuss about this connection, like from user clients to chat server connection, what type of connection we need. So user A is sending message to chat server and chat server is sending message to user B, or it's the connection is happening in by both the direction, right? So there are different types of mechanisms possible. First one is polling. So what happens since polling is user A, let's say, so I send the data to message to chat server. User B is the recipient. User B will keep polling the chat server in frequent intervals to ask like if there is any new message for me. If there is a new message, it will be sent to the user B. The problem with polling is the recipient has to ask again and again, a poll again and again to the server. The one improvement is long polling. What happens in long polling is, let's say there is this client and server. So here client will keep one connection open with the server, and when there is a response, when there is a message, server will send that, and after sending, client will create one more request. So it is slight improvement from polling. Now one more solution is server sent events. So let's say this is the client and server. So after this connection is established, server can send response to the client. So it is from server to client. So client cannot send message to server. So it will work for our system because server can send the message to the recipient using server sent events. And when some user will try to send a message, we can have a request response based connection. But the problem is we have to keep two types of connections in our system. Also, server sent events is not supported in all types of devices. The next solution is WebSockets. So here the client and server, after establishing the connection, both can send messages to each other. So this is a bidirectional connection. So and this is ideal for our problem. So here using WebSocket connection, the sender will send the message to chat server, and chat server using the WebSocket connection will send the message to the recipient. So I have improved the design with this WebSocket connection here. So we are having this stateful persistent connections to send and push messages instantly. Now let's quickly have a rough scale estimation. So consider there are 1 billion users and not everyone will be active every day, right? So there are 300 million daily active users, let's say, and 100 messages per day per user on an average. And also on an average, let's say each message will be 100 bytes. So 300 million daily active users, 100 messages per day and 100 bytes per message. 300 million is 300 into 10 power 6 into 10 power 4 bytes. So this is 10 power 12, 3 into 10 power 12 bytes, which is 3 terabyte. Now WhatsApp will not store the messages indefinitely in their system, right? So let's say they are storing, in the worst case, storing the undelivered message for around 1 month. So 3 TB storage per day. So that means 3 into 30, 90 terabyte per month. Now let's deep dive into few sections. So first of all, we have to scale the chat servers, right? So it will be auto scaled horizontally. Now the simplest scenario will be, let's say the sender and receiver both are connected to the same chat server instance. User A is connected to chat server 1 via this connection 1, user B is connected to chat server 1 via connection 2. Now it's easier, right? Because the message is coming to server 1 and is going out from the server 1 itself. So it's easier. But let's say this scenario where user A is connected to chat server 1 and user B is connected to chat server 2. So this mapping we can store locally in all the servers. But the problem is one user can get disconnected, right? And can again connect back with a say different chat server. So this is not ideal. So here I have improved the design. So let's say there are different WebSocket handlers and users are connected to this WebSocket, one of the WebSocket handler. And there is this WebSocket manager, it is storing this mapping, like which user is connected to which WebSocket handler. This mapping we are storing in this distributed cache. So let's say user A wants to send a message to user B, then the message will come to WebSocket handler 1 and the recipient is user B, right? So WebSocket manager will tell that user B is connected to handler 2. So the message will be sent to WebSocket handler 2 and WebSocket handler 2 then will send the message to user B. So that will be the flow. And also we want to store the message in database, right? So this chat server will take care of that. We can add one load balancer before that. as well. Now, how the WebSocket handlers talk to each other. So let's say user A is sending message to user B, the messages come to WebSocket handler 1 and we figured out that the recipient is connected to WebSocket handler 2. How the message will be transferred to WebSocket handler 2 so that this handler will send the message to the recipient. So for that I have introduced one Kafka here. So let's say if the message is coming from X to Y, so X is the sender and Y is the receiver, then the message will be added to a topic XY. See how it will work. So user A is connected to handler 1, user B is connected to handler 2, right? User A sends message to user B, then message will be added to topic AB. User B sends message to user A, then the message will be added to topic BA. Now, each WebSocket handler has two responsibilities. First, it has to receive messages from the users. Then, whatever messages is coming for this user, that also it has to receive, right, from this Kafka topic. So, this WebSocket handler 1 will be subscribing to topics where the messages for the user A, and WebSocket handler 2 will be subscribing to topics where the messages for user B. So WebSocket handler 1 will be subscribed to topic BA or all topics of the form XA to receive messages for A. WebSocket handler 2 will be subscribed to topic AB or all topics XB to receive messages for B. And this way, this WebSocket handlers will send the messages to each other. Now, these chat servers also can listen to these Kafka topics and store the messages in the chat DB. Now, one problem we have with this Kafka is not suitable for billions of topics, and there are billions of users in our system. So there will be billions of topics created in our Kafka, right, which Kafka is not suitable for. So we need some alternative here. So let's see what we can do. We can introduce one Redis PubSub here. The process will be same, but Redis PubSub is lightweight and it can have billions of channels. So the process is same. If user A is sending message to user B, it will be added to channel AB. If user B is sending to user A, it will be added to channel BA. And handler 1 is subscribed to all channels of the from XA to receive message for A, and handler 2 will be subscribed to all channels XB to receive messages for B. So all the processes is similar, but we have replaced Kafka with Redis PubSub, which is lightweight. But problem with Redis PubSub is it doesn't ensure guaranteed delivery. But we are good here because we are storing the message in the chat database for some time, right? So if it is not delivered to the user, it can be fetched from the database. Now let's discuss the last two requirements. The first one is last seen or online status of a person. So let's say when the user comes online or opens the chat app, so from the user client, heartbeat messages will be sent to the server. The messages will come to this WebSocket handler and then it will be sent to this presence server. So let's say the client is sending heartbeat messages every minute. And in this presence DB, we are storing the heartbeats of the user. So for user ID, what was the last heartbeat time? So, and also the status, whether the user is online or not. So based on the last heartbeat time, we'll decide whether the user is online or not. And if user is offline, when was the user last online? So that's it for this. Next, the last one is message sent, delivered or read status. So basically we see this ticks, right? Single tick, single gray tick, double gray tick and blue double tick, right? So how we see that? So let's say user A sends message to user B. So this is the flow, how this happens. A sends message to server first. So it's basically sender is writing the message to server. Next, server sends acknowledgement after receiving the message. So sender reads that acknowledgement and then we see the single gray tick. Next, message sent to user B. Then user B sends acknowledgement after receiving message. So receiver writes this acknowledgement. And then server sends acknowledgement to sender A that the message is delivered to recipient. So sender reads that acknowledgement and then we see a double gray tick. When user B opens the app and sees the message, reads the message, then user B sends acknowledgement after reading the message. So that is receiver is writing this acknowledgement to the server. Server then sends acknowledgement to sender A that the receiver has read the message and sender reads the acknowledgement. And then that's when we see the blue double tick that the receiver has read the message. So this is how this whole flow works. So not every user is interested in these days about these things, but this is one of the functionalities of WhatsApp or any other chat system. Now, apart from this message sent to user B, earlier also we are sending the message to user B, but only for this feature, we need extra read and write calls, right? We see 1, 2, and 3 write calls, and 1, 2, and 3 read calls. So there are 300 million daily active users, right? And 100 messages per day. So 300 million into 100 into 3 read requests per day. So that means 90 billion read requests per day. So 90,000 million, that is 90 billion read requests per day. And that is 90 into 10 power 9 divided by 10 power 5 read requests per second. If we assume approximately there are 10 power 5 seconds in a day. This is 9 into 10 power 5 or 90k read requests per second. Similarly, for writes, we need 90k write requests per second. So these are the extra requests we need for this feature. So with this, let's see if we have covered all our functional and non-functional requirements. Yeah, one-to-one messaging, group messaging, real-time message delivery, access messages after being offline, image and video sharing, online last seen, and send delivered send status. All the functionalities we have covered. Non-functional requirements, low latency message delivery via WebSocket connections, guaranteed delivery, of course, billions of users, each user sending average 100 messages per day, system is fault tolerant, and messages are not stored unnecessarily. So we have discussed all this and yeah, I think we are done with our system design here discussion here.